All right, this time we are going to do everybody's favorite problem type, which is the one that begins with use the limit definition of something. So here what we're going to do is we're going to use the limit definition of the integral to compute this integral from 0 to 2 of x squared dx. So maybe the first thing that I want to do is convince you of the fact that we can't use the geometry of the situation to actually compute this integral. So let's look at a small picture of what's going on here. So we have our function x squared between the x values of 0 and 2. And we know it's an upwards facing parabola. And so the area that we're interested in computing here, being the area between the curve and the x-axis, is this shape right here. Now, this is a parabola. It's not a circle, so we can't use anything about the areas of circles really to help us out here. This is also not a straight line, so we can't use anything about the areas of rectangles and triangles. So in fact, we kind of are stuck using this limit definition of the integral right now to actually compute this area. So this is going to be a new area computation for us. Certainly before this, or probably before this, we didn't know how to compute areas under parabolas. So this will be a nice kind of new ability for us, and something that in fact calculus gets us that we didn't have previously from something like geometry or something like algebra. So we want to use this limit definition, and we had better remind ourselves what that limit definition is. So I'm going to be using x squared as the function here, so we'll let f of x be x squared. And we want to remember that the integral from 0 to 2 of x squared dx is defined to be the limit as n goes to infinity of the sum from I equals 1 to n of f of xi dx, delta x. Great. So we want to work with this from the inside out, because right now a lot of these symbols don't mean very much to us. But we can do things like we can figure out what delta x is. We certainly know something about the function f, and we'll want to figure out what the xi's are as well a little bit later. But let's start by using the fact that we know what f does to its inputs. It squares them. So this is going to be the limit as n goes to infinity of this sum from I equals 1 to n. F of xi here is xi squared. Sorry, I seem to be having troubles with the zoom. Let's see, xi squared times delta x. Great. So let's think about what our xi's and what our delta x are by analyzing this interval from 0 to 2. So we have 0 to 2 here. And we want to have a formula for what delta x is and for what xi is. But these things depend on how many rectangles that we're creating. So we want to try to find a formula here that maybe depends a little bit on I, a little bit on n, in order to see what we can do to make this limit a little bit more tractable. So we'll first think about the case of what's going on when n equals 1. So n equals 1 means that we have one rectangle. And when we have one rectangle, well, that means that x0 had better be my left endpoint, and x1 had better be my right endpoint, and my delta x here is going to be 2. Great. Well, that tells us a little bit, but maybe not very much about what to do in the general case. So we'd better think about what's happening when n equals 2. If we're working with two rectangles, we need to have x0 here at the left endpoint. x1 falls squarely in the middle at x equals 1, and x2 falls at the right endpoint. So we have 0, 1, and 2 here. Our delta x this time, the difference between my x values, is going to be 1. Notice here that 1 is the length of this interval divided by the number of rectangles that I have. So the length of the interval is 2, the number of rectangles that I have is also 2, and that's going to give me the width here. If we move up to n equals 3, then we have x0 again at the left endpoint, but now we're splitting this interval up into 3 different pieces. So we have x1 here at 2/3, x2 here at 4/3, and x3 again at the right endpoint there. So we have 0, 2/3, 4/3, and maybe we could think about 2 as being 6/3. The delta x that I'm working with here, I'm going to stop writing delta x so that I have enough space to write this, is going to be 2/3, difference between those two x values, which again I can think about as being the length of the interval divided by the number of rectangles that I have. So in general, for the nth step, I'm going to have x0, I'm going to have an x1 all the way up to some xn, and maybe we want to include a random xi here in the middle. My x0 is always going to be at 0. My x1 is always going to be to the right. We're going to, again, take this interval of length 2, and we're splitting it up into n pieces. My x2 value will again be, well, I'm going to move it to the right by 2/n, so its x value is going to be 4/n. And we can see that the difference between my x values here is 2/n, so that's going to be my delta x at every n. The ith x value is going to be exactly 2i/n. We notice that I'm starting here at 2 times 0/n, 2 times 1/n, 2 times 2/n, and so on, and each x value is given by the formula 2i/n. So let's go back and use these facts that we have now in the sum that we're looking at here. We have a formula now for xi, we have a formula now for delta x. We want to actually apply these formulas and use them. So okay, let's separate that. So we have this limit here that we want to take as n goes to infinity. We have this sum from I equals 1 to n. And we know that the ith x value is given by 2i/n. And since we're squaring xi, we're going to square that 2i/n. Delta x, we found, was always going to be 2/n. And so we have some sum here. Well, let's go ahead and use some of the properties of sums to try to actually do this computation. So let's see. So again, we're going to have lim as n goes to infinity of this sum from I equals 1 to n. If I'm distributing the square into the different parts of the fractions, I've got 4i squared out of n squared times 2/n, which we can simplify a little bit. Lim as n goes to infinity, sum from I equals 1 to n of 4 times 2 is 8. I've got an I squared still in the denominator and an n cubed, or an I squared in the numerator, an n cubed in the denominator here. Now, something that we might want to notice here is maybe a better way of writing this, rather than writing 8i squared out of n cubed, is I'm going to choose to write this as 8 out of n cubed times I squared. Because what's happening is when we're doing this sum here, lim as n goes to infinity, we're starting with something like I equals 1. So we've got an 8/n cubed times 1 squared plus 8/n cubed times 2 squared, and so on all the way up until we get to n. 8/n cubed times n squared. But in each of these terms, I have this 8/n cubed sitting around. And the fact that I've got that in each of those terms means that I can factor it out of this sum. So I want to write this as lim as n goes to infinity of, let's get a better infinity there, lim as n goes to infinity of 8/n cubed times, well, now I've got 1 squared plus 2 squared plus, and so on, all the way up until I get to n squared. And it turns out that, similar to the video that we had last week where we talked about the sum of 1, 2, 3, 4, and so on, there's a formula for the sum from 1, 2, 3, of 1 squared, 2 squared, 3 squared, 4 squared, and so on. You don't need to know this formula for this class, but it is nice to know that a formula exists, and I'll go ahead and write it down here. lim as n goes to infinity, we have an 8 over n cubed out front, times the formula for this sum is going to be n times n plus 1 times 2n plus 1, all divided by 6. So we've taken this limit that we started with, the limit that involved our function f, it involved some delta x, it involved some ugly sum, and we simplified all of those different pieces until we have some formula here that we can actually take the limit of. If you do a little bit of arithmetic, and I'm going to skip this step because I trust you to expand polynomials, then what we get is the limit as n goes to infinity of not 8, we have 16 n cubed plus 24 n squared plus 8n, all divided by 6n cubed. So now what we notice is we have a limit of a rational function. I've got some polynomial here divided by some other polynomial. And if we're taking the limit as n goes to infinity of a rational function, we want to think about the degrees of the numerator and the denominator. The degree, being the largest exponent of my numerator, is 3. The degree of my denominator is also 3. And since these functions share the same degree, this limit as n goes to infinity is going to be the ratio of the leading terms. The only term that's going to matter as n goes to infinity here is the 16 over n cubed. The only term that's going to matter in the denominator, well, I guess there's only one term in the denominator, but it matters, and it's 6 over n cubed. And so this limit is going to be the ratio of these leading coefficients, this 16 divided by 6 here. You can also use L'Hopital's rule if you prefer that option for computing this limit. In any case, however you go about it, you're going to get that this limit is 16 over 6, which is 8 over 3. So all in all, after a whole lot of work, we find that this purple area here, underneath the curve of the function x squared, is about 8/3, which is a little bit less than 3. So we've now done something new with calculus, where we've, in fact, computed the area of some shape that we definitely couldn't have computed the area of before knowing any calculus.